Okay, hello everyone. Let us continue the third part of today's class. Excuse me. Okay, so we know that x is an should be the bold face. Okay, S is an n by m matrix Y excuse me. Okay, let us see what is the dimension of Y. Okay, we can see that we put the dependent variables in matrix Y. Okay, so let us go back to the first time we mentioned dependent variables. Okay, excuse me. Okay, so we can find that here. Okay, yi is a dependent variable whose value is found by observation. Okay, where I is equal to 1 to n. Okay, so I think y should not be a matrix. It should be a vector. Okay, so we should use the small y here. Okay. Okay, so of the matrix, this should be x. Okay, and vectors y okay, and and beta. Okay. Okay, so y should be a vector. Okay, I will. Okay, let us go to. Okay, I will fix the y and change it to a small y. Okay, in the handout later. Okay, I am sorry for the mistake. Okay, let us continue. Okay, so y is an n by n vector and beta. Okay, is and okay, beta is a vector, and what is the dimension of beta? Excuse me. Okay, we can let us find beta. The elements of beta is beta j, where j is equal to 1 to n. Okay, so we can know that beta is an m by n. M by 1 vector. Okay, so we have already known the dimensions. Okay, s of x, y, and beta. So let us go back to the slides. Handout. Okay, so in this equation, okay, the numerator is originally is the loss function L of d beta, So we can know that this is a scalar, okay, and beta is a vector. But then we have a problem. How do we find the partial derivative of a scalar with respect to a vector? Okay, let us see a Wikipedia page, okay, called matrix calculus. Okay, and according to this page, okay, we can find that, okay, scalar by vector. Okay, so the derivative of a scalar y by a vector x, which is equal to x1 x2 to xn transpose, is written, okay, in numerator layout notation as partial y over partial x is equal to this okay, excuse me, is equal to this vector, okay, partial y over partial x1 and partial y over partial x2, etc. to partial y over partial xn. Okay. Okay, then the second line of equation was 45 is, okay, let us see this equation. Okay, first we need a fraction, okay, here, and in the denominator is the partial, okay, partial oh, okay, it is strange. Okay, let us input the partial. Okay, here is let me see, partial, okay, here, okay, partial beta and partial, okay, and let us see the first term, okay, y transpose y. Okay, let me insert parenthesis, okay, y and transpose, oh sorry, transpose y, okay, y transpose y, and plus the second term. Okay, the second term, oh sorry, it is minus y transpose x beta. Excuse me. Okay, minus y transpose and x, okay, and beta. Okay, then the third term is minus beta transpose x transpose y, okay, minus beta transpose x, oh sorry, okay, minus beta transpose and x transpose, okay, and times y, okay, then the next term is plus beta transpose x beta, okay, so plus beta transpose x transpose, okay, and x, okay, excuse me, and beta. Okay. Then and we know that the partial derivative is a linear operator. So we can split this partial derivative into 4 partial derivatives. Okay, that is, please look at the blackboard. Okay, so it is equal to, the first term is the partial, over partial beta. And the first term is partial y transpose y. Minus the second term is partial y transpose x beta over partial beta, and then minus again then minus partial beta transpose x transpose y over partial beta, and finally, plus excuse me, finally the fourth term is partial beta transpose x beta over partial beta. Let me align at the equality sign. So I need to add an equality sign here, and I change the color of it to white. Very good. Let us call this equation 1. Align again. Let me align it again. Good, very good. So let us see the first term in equation 1. So when we do the partial derivative with respect to beta, so we can treat y and x as constant vector and matrix. So obviously, this term is equal to 0. This should be it is right. It is equal to 0. It should be a vector. 0 vector. Next, second, consider the following terms. Consider the second term in equation 1. So this term, and it is equal to, let us write down each element of y, x, and beta. So this partial derivative is equal to first y. So y is an m by 1 vector. So let us insert a pair of bracket. And then insert 3 box here. Okay, so it is equal to the first element is y1 and v dots and yn. Okay, good. Oh, do not have v dots. Okay, then we insert the dots. Okay, and don't forget we need to take the transpose. Okay, like this. And next, the matrix X. Okay, so let us insert a matrix. Okay, like this. Okay, and the first element is X 1 1. Okay. Okay, and the last element of the first row is, okay, please remember that X is an n by m matrix. Okay, so this element should be x1 m. Okay, like this. Okay, so this element should be xn1. Okay, and finally, this element should be xnm. Okay. Okay, and finally, the vector beta. Okay, and we know that beta is an n by 1 vector. Okay, so we can copy the vector y to here. Okay, and change it to beta. Oh, beta. What's wrong? Okay, so we need to insert the letter beta. Okay, Greek letter beta. Okay, and the last element is beta m. Okay. Okay, good. So the next step, it is natural to to transpose this vector. Okay. So the next step is this. Okay. We copy this and paste this here. Okay, y1 to yn transpose should then be changed to a row vector. Excuse me. Okay, so let me insert a pair of brackets first and insert 3 boxes. Okay, and the first term is y1. Oh, sorry. The first term is y1. Okay, and this is dots. Okay, and the last element is yn. Okay, so next step, it is natural to multiply this vector and this matrix together. Okay, so it is equal to, okay, partial over partial beta again. So before the multiplication, let us observe this is a 1 by n vector. Okay, and it is an n by m matrix. Okay, so the result should be a 1 by m vector. Okay, 1 by m vector. Okay, sure. So we let us copy this to here. Okay, and clear y1 and yn. Okay, so the first element of this vector is equal to y1 times x11 plus dots plus yn excuse me times xn1. Okay, so we can write it as a summation. Okay, let us see. Okay, summation. Okay, so first term is y1. Okay, times x11. Okay, and the last term is yn times xn1. Okay, so we can let I is equal to 1 to n. Okay, and we change it to I and change it to I. Okay, so good. Okay, I italic and n italic. So and so on, and the last term, last element of this vector is of the same form. Okay, and it becomes x1m to xnm. So we know that this term should be m. Okay. Okay, and finally the vector beta. Okay, here. Okay, good. Okay, next step. Okay, again it is equal to partial over partial beta. So next time it is natural to multiply this vector and this vector together. Okay, so let us see, this vector is a 1 by m vector, and this vector is a m by 1. Yes, m by 1 vector. So after we multiply these two vectors, we will get a scalar. Okay, so the scalar is equal to, okay, the first term is this term. This term. Okay, and times beta 1. Okay, and plus, okay, dots. Okay, then plus, okay, this term, and multiply by this term. Okay, beta m. Okay, like this. And let me put it into a pair of parentheses. Okay, good. Okay, so again we can write it into a double summation form. Okay, so first it is equal to partial over partial beta, and double summation. Okay, double summation. Excuse me. So the inner summation is again, it is I is equal to 1 to n. Okay, and the term in this is equal to yixi1 beta 1 to yixim beta m. So we can let a new variable j. Okay, and this also replaced by j. Okay, and it is equal to, okay, j is equal to 1 and to m. Okay, good. Okay, so then we need to do the matrix calculus. Okay, so we can know that partial y over partial x, it is equal to this vector. Okay, so let next it is equal to this vector. Okay, so a vector, and I need a pair of brackets. Okay, like this. Okay, it is 25 minutes. See you next time. Goodbye.